let's talk about complex numbers. It turned out that if in the previous lectures I mentioned that our work oftentimes involves real numbers most of the times, but sometimes we come across equations that do not have real number solutions. The solutions are going to be complex solutions. So the set of real numbers, it doesn't include all the numbers, it turns out, that we need in algebra. So for example, there is no real number solution to, if I want to solve x squared equals -1, there is no real number solution to this, because if I think of -1, you square it, you get 1. Or 1 squared is 1. Neither of these can be -1. So I've pretty much exhausted the possibilities for real number solution. So there's no real number solution to this one. So therefore we can extend the idea to complex numbers, and then we'll be able to solve solutions that are not real, unreal solutions, I guess. So before we do, actually, we need to recall what the imaginary unit is in complex number system. I stands for imaginary unit. And it's just that. I guess you can imagine, if you can imagine, square root of -1. This is just really a notation for square root of -1. All right, so that I squared becomes 1. Now, let me actually tell you that we're not supposed to be thinking I squared as I times I. I mean, that is fine, but not in a sense that I can do square root of -1 times square root of -1 and the answer becomes 1. That's not true. This one is okay. That one checks, right? I squared is I times I, but it's defined to be -1. Not because of the multiplication property of radicals, I guess is what I'm trying to say. So, there you have it. Once we have this, then we can define a whole class of numbers called complex numbers. So what are complex numbers? Well, complex numbers are numbers that are binomials, interestingly, and they're in this form. A plus bi. That's a complex number. Now in this, A and B are real. Okay, they're real numbers. Because if they're complex numbers, then you can work them, and ultimately we get into a form where A and B, again, we get another form of a complex number, and A and B end up being real. Okay, so might as well just call them real for now. Now, in this complex number A plus bi, A, we call A the real part. That's going to be the real part of that complex number. And B is the imaginary part. And remember, I is the imaginary unit. Imaginary part of that complex number. Okay. Now, some authors, some textbooks, some professors, BI for them is the imaginary part. Okay. Not just B, but B attached to I. Okay. So we can use them interchangeably. Now, since these are complex numbers, then we can actually add, subtract, multiply, and divide them. Now, example of complex numbers, by the way. For example, I can go 2 plus 3i. Square root of 2 minus 2/3 I. There you go. That's complex number. And so on and so forth. Now, if A is 0, by the way, if A is 0, let me actually give you the structure of our number system now that we talked about this. So if we think about our real number system, okay, so here we have real numbers. And we can break down real numbers into subsets, actually, or subgroups here. Let's call this irrational. And then we have rational, right? And along the list of rational numbers, then we can list all other types of numbers. So we have our integers here, and then we have the set of whole numbers, right? And we have our natural numbers. Now if you call natural numbers, these are 1, 2, 3 and so on. Our whole number is 0, 1, 2, 3 and so on, so it just has an additional 0 in there. Integers are just like whole numbers, except they also have opposite of those natural numbers. Rational numbers are in the form p over q, if you recall, such that p and q are integer. Now here's where you have your fractions and you have your decimals, terminating decimals that is, or non-terminating but repeating blocks of digits. Irrationals are right square root of 2 pi e, things like that. Okay, that's what those are. Now, you knew about this already. So let's actually extend this now to the set of what we call complex numbers. So here is at top of the food chain, we have complex numbers that are in the form a plus bi, binomial numbers. Now, if the imaginary unit, if b is 0, then the complex number reduces to a real number. Okay, in other words, there's nothing imaginary about it, it's very real. On the other hand, if a is 0, there's nothing real about this number. So the number is labeled as pure imaginary. Example of pure imaginary is simply 2i. Notice there's no real part to that. I can have pi I. So you don't have the binomial, you only have a monomial, but I must be there. Could be negative 2/3 I, and so on and so forth. And my pi doesn't look like a pi. There you go. All right, so that's what the structure of our complex number looks like. Now the a plus bi is the standard form. Okay, so when we talk about the standard form of complex number, it's going to be a plus bi. That's going to be the standard form. All right, now having done this, we can actually now proceed with working with these complex numbers. Now one thing that we can do, by the way, if you look at, for example, square root of -4, now we can do the following with it: square root of 4 times square root of -1. Remember the multiplication, the nth root of a, nth root of b, in one of our earlier lectures in the review, may have been review 7 or 8 when we did this. We mentioned that the nth root is ab, and we also emphasize that at least one of these must be real. The other one could be imaginary, but they both cannot be imaginary, or you get into a situation where you do square root of -1, root -1, you get 1, and that is not true. So if I look at square root of -4, this one is real and that one is imaginary. So I'm actually okay to do that. Now square root of 4 is 2, and square root of -1 by definition is I, so we can write this as 2i. Now again, the fact that I write it as 2i does not imply that I was able to find square root of -4 in the real number space. The answer is still imaginary. Okay, now let's see how we're going to actually add, subtract, multiply, and divide them. Okay, so addition, subtraction. Now the way to add and subtract these, because they're binomials, we're going to add just like we add binomials. So for example, let's say I have 3 -4i, and I'm going to add to this -2 plus 6i. Okay, well, I can do this by adding the real parts together. That's 3 plus -2, and add the imaginary part, -4i plus 6i together. And the result's going to be 1 on the real side and 2i on the imaginary side. And that would be the standard form. Remember, the standard form is a plus bi. And there you have it. Now to multiply these, we can actually multiply them. Let's see. Multiply them like we multiply binomials, right? Multiplication. So let's say I want to do 2 plus 3i times 5 plus 7i. And when I FOIL them, that's going to be 2 by 5, 10. 2 times 7, 14i. Plus. Then we're going to go 3 times 5 and 3 times 7. So that's 3 times 5 makes 15i. Plus 3i, 7i. That's 3i times 7i. And that's going to give us 10. 14 and 15 gives me 29i. Now, 3i, 7i, that gives me 21i squared. Okay, and that is the I squared. Now remember, I squared, we called it to be, by definition, we said I squared is going to be, what, -1? Okay, and we have that from our notation earlier. So I can write this as now 10 -21 plus 29i. And the whole thing is -11 plus 29i. And you got this one. Complex numbers. So addition, subtraction, multiplication is pretty straightforward. Something about multiplication, by the way. This is a really cool special case of multiplication. Suppose I have a plus bi. That's the standard form of a complex number. Then I have another complex number that's going to be what we call conjugate. Conjugate of a plus bi. These two binomials are conjugates of each other. Okay, so when we multiply two binomials that are conjugate, this is a general form, any two complex numbers. We're going to FOIL them, and when we FOIL them, we get a squared negative abi plus bi times a gives me another abi minus b squared I squared. The two middle terms are like terms and they're opposite, so they add to 0, leaving me with a squared negative b squared. But then I squared, remember we just said I squared is -1. So that makes this a squared plus b squared. And that's interesting because when we multiply complex conjugates, the result's going to be sum of two squares. And remember, when we talked about factoring in our review, we mentioned difference of two squares was factorable, but not sum of two squares, right? Well, sum of two squares is also factorable. There, we're looking at the factored form, a plus bi, a minus bi. But it is not factorable using real numbers. But if we allow for imaginary or complex numbers, then we can actually do that. Okay. Now, the reason I mentioned this, other than the fact that if we see something like sum of two squares, from now on, we're going to be able to factor them. Okay. And we'll be able to now do division of complex number. Now, division of complex number is numbers. It's kind of strange. Let me do an example. It looks nothing like a division, in fact. It's more of a process. Okay. So this is not going to do what you think it will. It's not going to work like this. So you're not going to divide real parts, imaginary parts. I wish it was that simple, but it turns out it doesn't work out that way. So how do they work out? Well, like I said, it looks nothing like a division. It's more of a process of transformation. And what we're doing is this. We're going to actually multiply. We're going to multiply the top and the bottom by complex conjugate of the denominator. So a plus bi, remember the conjugate is a minus bi. So the real part is exactly the same. You just make the imaginary unit, the imaginary part, opposite in sign. And there we have it. That's what they are. Now, in the numerator, we're going to multiply two complex numbers. So that's going to be 1 minus 3i times 1 minus I. In the denominator, we're going to multiply the conjugates. Let's do FOIL on top and the bottom. Remember, we showed, however, up here, when we multiply conjugates, the answer is going to be a squared b squared. It means you square the real part plus square the real imaginary part. That's if you don't want to use FOIL, you just want to jump right to the answer. I'm going to actually show the details for you. In the denominators, I'm going to get 1 minus I. Second distribution, I get plus I minus I squared. And remember, I squared is negative 1. So, and these add to 0. See, they always do. The middle terms, the OI, end up being opposites. So that's 1 plus 1. And the answer is going to be, again, plus 1, because you have a minus, and then minus from negative 1 makes positive. So the denominator is 2. In the numerator, we're going to FOIL. Again, distributive property, we get 1 minus I, negative 3i, negative 3i squared. And that's 1 minus 4i. Negative 3i squared becomes plus 3i. I'm sorry, plus 3, no I, because I squared is negative 1. And then we can write 3 plus 1 is 4 minus 4i divided by 2. Now remember, we want the answer in standard form. So to get to standard form, you divide 4 by 2, you get 2. The other 4 by 2 is also 2. And there is the standard form. The emphasis is on a plus bi form. And there you have that one. So as you can see, I mentioned it's not straightforward. It is a process when we try to divide complex numbers. Now, lucky we don't have to do much work with complex numbers in this course. We do look at it later on when we talk about zeros, or solutions to equations for polynomials. Some of the solutions may be complex or imaginary, and that's why we need to talk about these. All right, and the last thing I wanted to talk about in this lecture is actually powers of I. Now, the powers of I, we already seen I squared. But let's take a look at these powers of I. First, I to the first power is itself, right? We mentioned I squared is negative 1. So what if I want I cubed? I cubed, of course, by definition of exponential form, that's just I, which we can write it as I times I squared. I squared is negative 1. So stands to reason that I cubed should be I, right? I'm sorry, negative I, because this is negative 1. And indeed, that's true. I cubed ends up being negative I. So notice these are 3 different values so far. I squared, I cubed. Let's look at I to the 4th. I to the 4th is going to be product of, one way to think of it is I squared times I squared, or you can do any other combination. This would be the easiest one. Negative 1, the answer is 1. So very interesting. The even powers of I end up being real, either negative 1 or 1. The odd powers of I are imaginary, either I or negative I. Okay, so for example, let's say I want to do I to the 7th power. It's an odd power, so the answer is going to be either I or negative I. And let's see, I'm going to write it as I to the 4th times I cubed. I to the 4th is 1, we just showed that, and I cubed is negative I. So I to the 7th is negative I. So that's how we can do powers of I. Okay, if I want to do, I don't know, I to 57th power, I don't know why, but we could. Well, to do this, I'm going to see how many I to the 4th can I fit in 57. So let's see, 4, subtract, bring down the 7, 4 times 4, 16, subtract, remainder is 1, and quotient is 14. Now that quotient of 14, that just tells me that there are 14 whole groups that we can fit in I to 57th power. Okay. In other words, I can write this as I to the 4th to the 14th power. And that's going to pick up 56 i's, right? And I still have the remainder, one more I down here. Now, I to the 4th is 1, so we just know that that's 1 to the 14 times I, and the answer is going to be I, because 1 to any power is 1. And there you go. Odd powers of I, the answer is either I or negative I. Even powers are either 1 or negative 1, because of the pairing effect. And that's all in this section. Now let me make up some examples. And let's take a look at these examples together. So for example, let's say I want to find square root of negative 25. I can write this, by the way. And this is usually what we do. We're going to write that as root 25i. Now how? Why? Because I can write this as 25 times negative 1 and use the product rule of radicals. That's square root of 25 times I, because square root of negative 1 is I. And there you go. So anytime you have square roots where radicand is negative, just change it to a positive, but remember to put I in front. And square root of 25 is 5, so the answer is going to be 5i. And there you go. That's the real number, and I. Let's do a multiplication. I'm going to multiply, let's say, negative 13 times square root of negative 13. Again, I want to emphasize we are not allowed to do this. We cannot multiply them because this is imaginary, so is that. We have two not reals, so we cannot do this. Then what is the correct way of doing it? We're going to write this as root 13i times another root 13i. Now root 13 times root 13, if you want to write it, that's root 169. But anytime you multiply two square roots where the radicands are the same, you simply get the radicand. When you multiply two square roots, you get the radicand back. You can see here square root of 169 is 13. So you could multiply them, then take the root, or just do the shortcut. And I multiplies by I, right? Those two. And I is I squared, so the answer is going to be negative 13, because I squared is negative 1. Keep that in mind for now. And there we have the product of them. Let's look at let's do a fraction. Negative 24 over square root of 8. Again, I can write this as 24i square root over square root of 8. And now I can actually combine 24 and 8 as a fraction. That's 24 eighths, and then the I is on the outside. That's square root of 24 divided by 8 is 3, so that will be square root of 3i. And there you have that one. Okay, so the answer is going to be pure imaginary. Now let's take a look at another one. How about if I get something like this? Suppose I have, let's say I have 10 plus square root of negative 200. Then I'm going to divide that by 5. Okay, so first I can divide 10 by 5 plus square root of negative 200 divided by 5. Now 10 divided by 5 is 2. Now square root of 200, let's work on that one. Square root of negative 200. Well, for one thing, remember we write it as a positive, bring I in front. Now 200, the easiest way to resolve that one, the largest perfect square in 200 is 100. Square root of 100 is 10, 2 remains, and I is in front. So that's going to be plus 10 root 2I, and then divided by 5, right? Because denominator is 5, divided by 5. Now 10 divided by 5, those cross. The answer is going to be 2 plus 2 root 2I. And there we have that one, number 43. Okay. This was one of the exercises I happened to look at. It was number 43 in the homework problems I was looking at. Okay, now let me make an example of a difference. So let's say now I want negative 2 plus 4I, something simple. Negative 5 plus 7I, something like that. Now to do subtraction again, we're going to remove parentheses. We're going to distribute the sign, negative 5 minus 7I. And once we do, the next step, we're going to combine like terms. Real parts and imaginary parts. There, 4 minus 7 is 3. Negative 3 that is, so the answer is negative 7 minus 3I. Let's see, let's do another one of the products. I'm going to do a conjugate. 3 plus I, 3 minus I. And remember, conjugate A plus BI, A minus BI. Let's get used to this formula. Gives you a sum of two squares. So you square the real part plus, don't worry about the I. B, well, I is 1 times I, right? So when we square the real part, B is 1 here, it's plus 1 squared. That's going to be 9 plus 1. The answer is 10. Okay, so that one answer is 10. And let's do a division. Suppose I have 1 minus 3I over 1 plus I. Remember, to divide, it is a process. We're going to multiply top bottom by conjugate. In the denominator, we get 1 squared plus 1 squared, right? Because I times negative I is negative I squared. You can FOIL if you like to. I just use, and this is special product. Okay. Now in the numerator, we have to FOIL it, right? So I'm going to do that. 1 times 1 minus I is 1 minus I. Negative 3I times 1, and negative 3I times I is I squared. You can do again the same thing in the denominator. That's 1 minus 4I plus 3 divided by 2 makes 4. Negative 4I divided by 2, and 4 by 2 is 2. Got to remember to divide, by the way, both of these by 2, not just the first one. And that's going to be 2I. Okay, so we're done with this division. Now let's take a look at doing maybe a couple of powers of I. Okay, so in this next example, we want to do, for instance, I to the 23rd power. Again, the key is to break that exponent into as many groups of size 4. That is I to the 4th. 5 times 4, 20 in this case. When I have 23 i's, that means I can have 5 groups of I to the 4th. Okay, and 3 i's remain, so I'm going to go I cubed. Right, that's the remainder. Now I to the 4th is 1, that's 1 to the 5th, and I cubed was negative I. So the answer is negative I. Again, we don't really have any practical uses for this in the work we're doing. We're just playing around and just having fun with this. What if I have I, let's say we have something like I to negative 14th power. So I'm just going to check out the negative exponent here. Now, first we need to rewrite this using positive exponents. So using negative exponent rule, that's 1 over I to the 14th power. Now we can work I to the 14th separately. And that's I to the 4th cubed. That will pick up 12 i's times another 2 factors of I. And that's 1 times I squared negative 1 is negative 1. So the denominator is just negative 1. The whole thing, positive by negative, it's going to be negative. The answer is negative 1. All right. And there you have it. I think that's good enough for our work. So this is how we handle complex numbers. Again, as long as you recognize them, you know how to work with them on the basic level. That's all that concerns us. Again, thank you for watching this video.